So you had a question about problem 148? Ah, okay, so. You're fine. Okay, so this is a mission 10 question, which is fine. 148. Let's see here. I give you I equals dq dt, right? So the change in charge per time. And I give you that that's equal to 10 times 1 minus e to the minus 2t. All right. And then I say calculate net charge zero less than or equal to t less than or equal to 3. So the context here is that we're talking about like a circuit, an electrical circuit. So the way it works is that, you know, you have some kind of like wire, right? And you're talking about like there's a particular point in the wire, and the current is the charge that flows past that point, right? So you're adding up the net charge that flows past that point. That's what the question's asking for, all right? Now, technically, I can't answer your question yet because we haven't gotten through this material. So, I mean, can I come back to this once we get to it today? Yeah. The reason I can't quite, I mean, there's parts of it I can answer. Like, okay, so we have FTC2, right? What did FTC2 say? It said that if f prime of x is equal to f of x, then the integral from a to b, I'll write over here, the integral from a to b of little f of x dx is equal to f of x evaluated from a to b, right? And this notation means f of b minus f of a, right? And so that is the fundamental theorem of calculus part 2. That is the tool we're going to use to calculate integrals, right? Now, the other idea I need here is an application. So this is sometimes called the net change theorem. And it's really almost just FTC2 again in a particular context. And here goes. If we want to integrate, say from time 1 to time 2, a rate of change. So let's say dy dt. So let's think about this. If I'm going to integrate dy dt, what's the antiderivative of dy dt? Like what function, when differentiated, gives me dy dt? Well, just y, right? So I do y of t evaluated from t1 to t2. In other words, it's y of t2 minus y of t1. So if I want the net change in y, so you could call this delta y if you like, the change in y, the net change in y. We can get the net change in y by integrating the derivative of y with respect to time over the time interval. All right? And formally, like, this kind of makes sense, right? Because here, if you can think about canceling the dt's, what would it give you? Right, so this would be equal to the integral of dy. But to be fair, we're doing a definite integral. And one of the things we're going to learn as we go on here is that if you change the variable of integration, so I'm changing the variable of integration here from t to y. So to be fair, you have to change the bounds of the integration in the same way. So it'd be y of t1 and y of t2. Those are the corresponding bounds in y. But what's the integral of dy? It's just y. So you have y evaluated from y of t1 to y of t2, which is what? Well, it's y of t2, y of t1, so now we've come full circle or full square, however you want to look at it. So, correct. So for problem 148, what we want to do to calculate the net charge is we want to calculate the integral from 0 to 3 of dq dt. So the answer, the net change in the charge should be the integral from 0 to 3 of dq dt, right? But the reason we're hung up at that point on that is because this function here has something we don't know how to integrate yet. We haven't talked about how to integrate e to the minus 2t just yet. Okay? What's that?
Huh?
What was that?
Oh, no, I'll really it's not good.
Oh, okay. It's all good. So anyway, I'm going to just leave this here and we'll come back to it, okay? So we need to talk about applications of integration, right? And so, like, number one, you guys tell me, what is the integral from a to b of f of x dx? What does that give us? That is true. It is big F of a, big F of b minus big F of a. That is true. But like conceptually, what is this quantity? Remember the whole discussion? It is a number, whatever it is. But if I drew a graph, if this is a and this is b, what is the significance of that? What constant is that? What does that number represent? The what? Not the area, but the signed area, right? This is the signed area that we're looking for? Yeah. Possibly. That's the signed area, right? So if you're asked a question, find the area bounded by this curve, you got to be careful because you might not just be able to just straight integrate. So let me show you an example of this, where the signed aspect of it matters. Find area bounded by y equals to, say, sine of x for 0 less than or equal to x less than or equal to 2 pi. Right? So if we just integrated from 0 to 2 pi, we saw what happened last time, right? What's the antiderivative of sine? Negative cosine. We got minus cosine of x evaluated from 0 to 2 pi, which is minus cosine of 2 pi minus a minus cosine of 0, also known as minus 1 plus 1, 0. So the area bounded by y equals sine of x from 0 to 2 pi is 0. But this is false, right? This is false because the area bounded by sine of x, well, y equal, I should, to be more complete, I should say bounded by y equals sine of x and the x-axis. That's really what I mean to say here. If I draw a picture of that, sine of x looks like this, right? And so the reason we're getting 0 is because we're not calculating the area, actually. We're calculating the signed area, right? And so the signed area isn't what I was asked for here, is it? So, one thing we should notice is that find area bounded by y equals f of x and y equals 0 for a less than or equal to x less than or equal to b. Instead, calculate the integral from a to b of the absolute value of f of x dx. That's a simple, way to adjust for this problem, right? If we take the absolute value, it takes the part of the function which is negative and turns it over, right? So like, this is y equals sine x, right? If I take absolute value, what's it look like? Right. So how are we going to, and how are we going to do that kind of integral? Like we integrate from 0 to 2 pi, the absolute value sine of x dx. So
would just be negative cosine?
well, it's absolute value though, so it depends. So this is just negative. I mean, let me break it up into two pieces. So this is the integral from 0 to pi of sine of x dx plus the absolute value. The integral from pi to 2 pi of the absolute value sine x dx. Like logically, that's the first step, is I can break it into this integral plus that. And the reason I've done that is because those are the two places where I can break up the absolute value of sine. So like absolute value sine of x is just straight up sine x. Come on, chalk. So this piece is straight up that piece, right? And so that's given by this integral. But yeah, the other one's what? Right.
Yeah, I get why it's set up like that. That makes sense.
So pi to 2 pi, but this time the absolute value sine x is minus sine x, because that's where sine is negative. See? From pi to 2 pi, it's this piece right here. See, that's where sine of x is negative. So absolute value does something there. It changes sine to minus sine. For example, 3 pi over 2. Sine of 3 pi over 2 is minus 1. So I would do minus and minus 1 to make it positive, And now we can, this one is minus cosine x. The antiderivative is minus cosine x. But this one, the antiderivative is cosine. And I got to be careful of my bounds, pi to 2 pi. And so what happens? You've got yourself minus cosine of pi plus cosine of 0 plus the cosine of 2 pi minus the cosine of pi. Yeah, cosine of 0 is 1, cosine of 2 pi is 1, cosine of pi is minus 1. So what you got here is 1 plus 1 plus 1 plus 1. You got 4. Now remember last time, one of the first examples we did was we calculated that the integral under the first loop, like under the first hump of sine was 2. Remember? So this is completely unsurprising because last time we proved, in fact, that the area here was 2, and by the symmetry of the problem, of course the area bounded by the negative part of sine is the same. The signed area is -2, right? So if the signed area is -2, then that means the area between, that and that is actually 2. Area has to be positive is the thing, all right? So now, is this the right, I wanted to show you this way because I wanted to show you all of the steps, right? But if I was a student and I faced this problem on a test, I would just go by the symmetry of the problem, this is equal to twice the integral from 0 to pi of sine of x dx, I would have just done that personally because it's just sort of almost obvious, but. So that's the first thing, is we can talk about area versus signed area, all right? Areas have to be positive, that's right. Another application of integration that we like to talk about in this course is the average of a function. All right? So here's the definition. F average is going to be equal to 1 over b minus a, the integral of f of x dx from a to b. So to calculate the average of a function, we just integrate and divide by the length of the integration region. So just to give you an example, average calculation. How about this? Find f average for f of x equals x squared, 0 less than or equal to x less than or equal to, let's say, 2. So here we go. We just, follow the definition. F average. So this b over, so this is the a. This is the b, right? So we have 1 over the length of the integration region, which is just 2. Integrate from 0 to 2, x squared dx. So we do 1/2. What's the antiderivative of x squared? That's derivative, but antiderivative.
1/2 x?
No? Remember, we do integral of x to the n dx, 1 over n plus 1, x to the n plus 1, plus a constant. So here n equals to 2. So we do 1 over 2 plus 1, which is 3, 1/3 x cubed. That's the antiderivative, right? 1/3 x cubed. Then we got to evaluate that thing from 0 to 2. And so that is 1/2 of 1/3 of 2 cubed, right? Minus 1/3 is 0. Which is what? That's 8 over 2 is 4. So apparently 4/3. The average of x squared from 0 to 2 is 4/3. Does that make sense? let me talk here for a minute about what the concept of the average of a function means geometrically, all right? So the graph of y equals x squared, it goes where it goes. It goes to 1, 1. It starts at 0, 0, right? And when you get to 2, where is it? It's up here at 2, 4, right? So the graph of y equals x squared looks something like this, right? Where is 4/3 in this story? What is 4/3? In a decimal, that's like what, 1.33333, right? So on my graph, where is that line, y equals 4/3? Yeah, just above 1, like right in here, right? Here's f average. So what's the significance of the average value of a function? I mean, it is what it sounds like. It's the average value, right? But if you wanted me to say something more, I could say this. I could say that the area below the average, right? At least for a positive function. For a positive function, well, I guess it's always true. The area bounded below the average is going to be equal to the area bounded above. Like this area, the yellow and the white areas have to match. Should be equal. I believe so. Yeah. I guess we could check. How would you check my claim? Yeah. Well, anyway, let's see if I can work another one here. What's the average of like cosine? Let's say cosine x for 0 less than or equal to x less than or equal to 2 pi. So f average is what? 1 over 2 pi in this case. Integration from 0 to 2 pi. Cosine x dx. The antiderivative of cosine is sine, right?
When is it negative sine?
The derivative of cosine is negative sine. The antiderivative of cosine is sine because sine differentiates to cosine. Yeah. So we get sine of 2 pi minus the sine of 0, but, well, these are both, they're both what? They're both 0, actually. Sine of 2 pi is 0, sine of 0 is 0. So the answer here is 0. But this makes a lot of sense, because what does the graph of cosine look like from 0 to 2 pi? Well, it starts out at 1, right? Then it does this, right? It goes back to where it started. right? So this piece right here, right? And once again, so maybe you can better believe my claim here that the average, if we draw y equals the average, that's the line for which there's an equal amount of area above and below, right? I mean, I'm not saying that right. The area above, I guess the area bounded between y equals f average and y equals f of x above is equal to the area bounded below by those two. I may still be saying it wrong, but you can see what I'm saying, even if I can't find the words to say it precisely at the moment. All right. In physics, there is another kind of average. Well, not just in physics, but so how can I say this? Can you guys tell me another kind of average besides, like, how would you take an average before you knew integral calculus? Like, if I had a class and I tell you that one person gets a 90%, another person gets a 95, and the third person gets 100, how would you calculate the average of their grades? No, I'm just asking, if you have 3 grades, how do you average them? Add 3 and divide by 3, right? So why didn't we just add the values of the function and divide by the number of values? Well, if you're thinking about a continuum from A to B, right? How many different values does the function take from A to B? Infinitely many, right? So we can't just divide by the number of values. We have to rely on the integration, which is the next best thing. This kind of gives us the sum of the values, and then we divide by the number of values, quote unquote, by b minus a. I mean, this is the continuous extension of the concept of average. But if you want to take so I've been doing averages of functions of x, right? But we can also talk about the average, if we have a function of time, right? Function of time, then time average over, t1 less or equal to t less or equal to t2 is given by, So I'm not saying anything different here. I'm just saying that this would be like a time average. If you had a continuous function, whatever it was, let's say y, find f of t. So if we're a function of time, we divide by the duration, the time interval, right? So one interesting place where this comes up in like freshman physics is the following example. Remember we had this before? We had that if the acceleration was equal to minus g, we worked out that the velocity as a function of time was equal to, what was it? V naught minus gt, right? That was the formula we worked out. And so now we can ask, how does, v1 plus v2 over 2 compare to the average for t1 less than or equal to t less than or equal to t2? In other words, we can compare just the average, like some people might call this the geometric average, or the arithmetic average, to this integration average. And the funny thing is, well, let's see how it works out. So how would we calculate the average in this case? We do 1 over T2 minus T1, right? Integrate from T1 to T2 of our formula, which was V naught minus GT. So we get 1 over T2 minus T1. And what's the antiderivative of V naught? Well, it's V naught T. What's the antiderivative of minus 1/2 GT? It's minus GT. It's minus 1/2 GT squared. I evaluate that from T1 to T2. And so what I got here is 1 over T2 minus T1, V naught times T2 minus T1, minus 1/2 G T2 squared minus T1 squared. And you do the algebra here, you can factor out a T2 minus T1, and we're left with V naught minus G times, well, T1 plus T2 over 2. Now, let me just kind of unpack what I just did there. So what I did was I factored this guy into T2 minus T1 times T2 plus T1, because it's the difference of squares. So if I do that, I can see that I have a T2 minus T1 factor for both of those terms. So I can factor it out, and then they cancel, right? And then if I want to write everything as a half, I've got, well, 2 V naught minus G times T1 plus T2 over 2. And then one more step. This is 1/2 of V naught minus GT1 plus V naught minus GT2 but I would point out that the first term, this one is V of T1, and this is V of T2. So in physics, you usually just say that this is quote unquote V1, and you usually just call this V2. And so what you're looking at is V1 plus V2 over 2. So what does this mean? This means that in constant acceleration physics, the average velocity in the sense of integral calculus that we introduced today also is equal to the average of the velocities at the endpoints. This is very fortunate, and although I will say you're very unfortunate if you have a problem in physics where you need to use this, there's an elite class of more horrible homework problems which require this understanding. And I have not assigned you any of them because this is not physics, you know? All right, so trying to think. So there's the net change theorem, calculating areas bounded by curves. I suppose I could show you. There's one other application that maybe we'll cover maybe next week. I don't think. Let me just take a quick gander here. Oh, no, problem 154 and problem 155 require me to discuss another example or two here. So I better do that. But I want to answer your question. So I'll tell you what, I'm going to put off. So I will just tell you this. You can skip problem 154 and 150. Like, don't try to do problem 154 and 155 just yet. The homework mission 10, I put a revised schedule out last night in the wee hours of the morning, and like that's due next Friday. So we'll have Monday and Tuesday, listen to me, Monday and Wednesday talk about those. So I'll cover some example Monday, hopefully, which looks like, problem 154 and 155. So I'm going to save some of the applications integral calculus for Monday. The last half-hour class today, or 40 minutes or so, since we have time, I will focus on the problem of U-substitution, all right? Because that's the other major calculational skill we have in here. And once you understand that, you'll be able to work a vast number of the remaining homework problems, all right? Including problem 148. Let's see here. All right. Can I erase? Yeah. All right, so let's talk about, where'd my chalk go? Ah, here it is. U-substitution, aka the chain rule for integration. All right. So essentially, this is the closest thing we have to the chain rule for integration. And I don't think I'm going to prove it for you. I think instead of proving it for you, I'm just going to show you how we do it. All right? So here we go. Example 1. And I will, so before I even do that though, let me give you just the algorithm. So here's the steps. Number 1, you choose a substitution variable. U, all right? And what I mean by that is we're thinking of U equals to stuff in the given variable, all right? Typically in X. But if we started with an integral in T, U would be equal to stuff in T, right? And number 2, we calculate du dx equals to whatever, and we trade dx for du and appropriate terms. I'm being deliberately a little bit vague here. And then 3, we calculate the integral in terms of u. And step 4, so we go back to original variable. That's the game plan. So, example 1. Suppose we have to integrate e to the x times the cosine of e to the x dx. Now, I will point out to you, this is not one of the ones we've done before, right? But what we're going to do is we're going to make a U-substitution. So we're going to say, okay, let's try u equals to e to the x, right? Then what's du dx if u equals e to the x? Du dx is e to the x, right? No, I'm differentiating. So I would point out from this, we can get that du is equal to e to the x dx, right? See that? Du is e to the x dx. Check it out. So e to the x dx is this one times that one, right? So I can rewrite e to the x times dx as du. And what's this? E to the x is u, right? So what we have here is cosine of u du. And then, so typically I put a little thought bubble over here and put an arrow. If you look at my solutions, I typically do that. All right? So I write off to the side my thinking for the substitution. And then, so I did step number 1, I did step number 2. All right? Now, step number 3, calculate the integral in terms of u. So for this method to work, after we make the u substitution, it's got to be something we already know how to integrate, which is the case here. Cosine of u, we know how to integrate. It's what? It's sine of what? Sine u, right? So this is sine u plus a constant. And then step 4, go back to the original variable. So that's the sine of e to the x plus a constant. And there you go. We have to learn what the derivative of the substitution variable is, how it relates to the original variable. Let's do another. But yes, there is differentiation involved. It's true, yes. How about this? What if we have the integral of x cubed sine, oh, how about hyperbolic sine of x to the 4th dx? I'm going to do this one a little bit different than I did the last one. All right, so you guys tell me, what should I make u equal to what? X to the 4th. I think that's a very good choice. If we make u equal to x to the 4th, what's du dx equal to? Mm-hmm. But it's 4x cubed, right? We got to bring the 4 down and then, yeah, the power rule for differentiation. Right. Now, so sometimes the way people like to do this is they like to solve du dx for dx. Solve du dx for dx. What's this tell me dx is equal to? Dx is equal to du over 4x cubed, right? So I just, basically, did I do that right? Oh, I'm an idiot. Oh, I'm a dummy. Sorry about that. No, I'm right. I multiply dx over here and divide by that over there. Just think of them, you can literally think of them as fractions. Right. So what we got then is the integral of x cubed, right? Sinh of what? This was u. And dx is what? du over 4x cubed, right? So if we make a wise choice for the u substitution, when we substitute in the u, the x's ought to cancel out, right? So see how that happens? X cubed cancels x cubed, and we're left with 1/4 integral of the hyperbolic sine of u du. Well, we have to know that the integral of sinh is cosh. So we get 1/4 cosh of u plus a constant. And then we go back to x, right? So the answer is 1/4 hyperbolic cosine of x to the power 4 plus a constant. And there you go. Mm-hmm. What happens if you use x to the third? Bad things. Bad things, because then x to the fourth, what is x to the fourth in terms of x to the third? I mean, you got this x to the fourth here, right? If you say u equals to x cubed, right? To get to x to the fourth, I need to take u to the fourth, 4/3, I think. So I would get a sinh of u to the 4/3 if I wanted to substitute in u equals x cubed. And that's a bad place to be, because we do not know how to integrate sinh of u to a fractional power. Like it's Now that is a good question. So his question is, how do we decide what u is? You're not going to like my answer. Guess. But it's intuition guided by experience. The more you know, the better you'll get at guessing. So, I mean, well, the other answer to your question is try something, and if it works, good. And if it doesn't, try again. How about tangent? I'll do theta this time. Tangent of theta d theta. So this one, what we need to do is we need to go, oh, well, wait a second here. This is integral of sine theta d theta over cosine theta, right? Because that's tangent. U equals what here? You got two choices, basically, right? Two kind of like obvious choices. U equals sine or U equals cosine. But you got to remember that we have to substitute both the integrand and the measure. So the measure part I'm talking about is changing the d theta here to du, right? So I think we should use cosine, and I'll show you why. If we let u equal to cosine, then du d theta is what? Du d theta is minus sine theta, right? So this tells me that minus du is equal to sine theta d theta. Now that's a beautiful thing because sine theta d theta is just sitting there, right? This sine theta d theta, it's right here, right? So sine theta d theta is just straight up minus du. And the cosine theta is u. So we're left with minus du over u. And so what do we got? We got minus the integral. So what's the integral of 1 over u? It is the natural log of the absolute value of u. This is that special case that the power rule for integration fails, right? The n equals minus 1 case. So this is minus the natural log of the absolute value of u plus a constant. So by the way, one of the things I always encourage my students to do at this juncture in the course is to go through your basic list of integrals and write it down in terms of u, because you're going to need to use it in terms of u. And it's a helpful exercise also just to like get yourself in the way of thinking. So I mean, I'll start you out. Integral of u to the n du, 1 over n plus 1, u to the n plus 1 plus a constant, right? N not equal to minus 1. Integral of du over u, natural log of the absolute value of u plus a constant, right? Integral of e to the u du, e to the u plus a constant. And so the story goes, integral of du over 1 plus u squared, inverse tangent of u plus a constant, right? And so the story goes. There's like 20 of these basic ones that we need to know cold, right? I've made the list before with formulas in X. It's a good practice for you to go back to that lecture we did and just go through and change the X's to U's just so you have it in your mind's eye what the formula looks like in U, because you don't want to let that be the hindrance for doing the step, right? I mean, like some of us, we can get over-reliant on formulas in X if we're not careful. So this is minus the natural log of the absolute value of cosine theta plus a constant, right? What happens if you bring the minus inside the natural log? What does minus inside natural log do? What is it? Remember natural log of, a to the p is p times the natural log of a, right? So if I bring a minus, it makes it a reciprocal. So this is equal to natural log of 1 over the absolute value of cosine theta, right? So what did you say? Did you say a secant? Yeah. So I think I told you guys this a few classes ago, but now we've derived it. We can derive this formula for the integral of tangent using U-substitution. So let us take a second here to contrast my methodology. In example 1 and example 3, what I did was I found an expression which related du to the existing integrand that was convenient for me. In example 1, I found e to the x dx was du. In example 3, I found that sine theta d theta was minus du. Those were convenient because those expressions are just sitting there and looking me in the face in the original integrand, right? In contrast, in example 2, I solved for dx. I plugged it in, and I let the algebra cancel out. These are two different paths you can go down. You can either try to see how to substitute in, right? Or more mechanically and less elegantly, you can always solve for dx and plug it in and see if it works. the more elegant way is faster. The solving for dx way, you're less likely to get lost, but it takes more writing. So like, it's up to you which notation you want to follow. Let us do another example. Example 4, we will calculate, we'll finish this problem 148, all right? And up to this point, my first 3 examples, there were no bounds, right? So they were just indefinite integrals. But example 4, since it's tied to this homework problem, we're going to have to change bounds. All right? Well, actually, there's 2 choices, but anyway, here we go. So as we discussed before, the net charge that passes, delta Q, is equal to the integral from 0 to 3 of dq dt. But what are we given here? What was dq dt equal to? It was equal to 10 times 1 minus e to the minus 2t, right? So what I would suggest here is we make a u equals to minus 2t substitution. Let u equal minus 2t. I use the most people I've ever seen here on a Friday. So a steady stream of people. All right, so if we let u equal minus 2t, then du is minus 2 dt, right? So I'll solve for dt this time. Du over minus 2, right? So we have 10, 1 minus e to the u times du over minus 2. Now, I should emphasize here, if we're going to keep it a definite integral, we have to change the bounds. So u of 0 is minus 2 times 0, which is still 0. So I say we have to change the bounds, but that's kind of a empty statement for 0, because 0 goes to 0. But u of 3, well, that's more interesting. That gives us minus 6. So we integrate from 0 to minus 6. And we can do this integral because everything here is elementary. So let me just go through it. 0 to minus 6. So this gives me what? That's a minus 5, right? Minus 5 times 1 minus e to the u du. So we have minus 5 plus 5 e to the u du, which is minus 5u plus 5 e to the u, evaluated from 0 to minus 6 by the fundamental theorem of calculus, part 2.